The most distant galaxy ever confirmed sent us its light 13.4 billion years ago from a spot in space that has since drifted, carried by the universe's own expansion, to somewhere around 33 billion light-years away. Those are two different answers to the same question, and both are correct at once. That gap between them is the real subject here. What distance even means once the thing doing the measuring, space itself, refuses to sit still. Getting to that number took most of a century of careful work, an evolving ladder of measurements, a redshift written into the light of every atom, and eventually a gold-coated mirror parked 1.5 million kilometers from Earth, cold enough and patient enough to catch light too faint and too red for any instrument before it. Along the way, astronomers kept finding galaxies brighter and more mature than their own models expected them to be this early, and had to ask whether the records they kept breaking actually made sense. What follows tracks that light from a clump of young stars forming a few 100 million years after the Big Bang to a telescope orbiting the Sun today, asking at every step what it actually means to say something is far away. 300 million years after the Big Bang, the universe is dark in a literal sense. The first atoms have only just formed, hydrogen and a trace of helium, cooled enough from the heat of the beginning to stop being an opaque plasma and start being a transparent gas, and no star has yet switched on to push back against that darkness. Space is filled with faint clouds of this primordial gas, thicker in some places than others, and in the densest clumps gravity is doing what gravity always does, pulling matter toward itself slowly, across tens of millions of years. In one such clump, enough gas gathers that its own core begins to heat under the crush of its own weight. Pressure and temperature climb until hydrogen nuclei, forced close enough together, begin fusing into helium, releasing energy as light. A star has switched on. It is not alone for long. The same cloud that fed it holds enough material for thousands more, and within a few tens of millions of years a loose cluster of these first-generation stars, astronomers call them population 3, meaning simply the third and oldest population, has ignited inside the gas cloud that made them. These stars are unlike anything alive in the universe today, built from gas containing almost nothing but hydrogen and helium, with none of the heavier elements, the carbon, oxygen and iron, that later generations of stars would need to cool and fragment efficiently. Without those heavier elements to help gas clouds cool and collapse into smaller, gentler pieces, the clumps that do form tend to make unusually large, unusually hot, unusually short-lived stars, some of them many tens of times the mass of the Sun. Those stars are extravagantly bright in ultraviolet light, and that light does something specific to the gas around it. Hydrogen atoms, struck by enough ultraviolet energy, lose their electrons, a process called ionization. A bubble of ionized, transparent gas grows outward around each cluster of young stars, eating into the darker neutral hydrogen that still fills most of the universe. Multiply this by every star-forming clump across the young cosmos, and you get what astronomers call the epoch of reionization. A period lasting several 100 million years during which the universe's hydrogen gas, essentially all of it, is stripped of its electrons and turned transparent to the light these earliest galaxies are producing. Before reionization finished, ultraviolet light struggled to travel far without being absorbed by the surrounding neutral gas, the way fog swallows a headlight. After it, the same light could cross the universe largely unimpeded. The clump of stars this account follows is one of the more vigorous ones, not a single lonely cluster, but a young, chaotic collection of star-forming clumps loosely bound by gravity, still growing, still merging with neighbouring clumps of gas and stars. Call it a protogalaxy, a galaxy still in the process of becoming one, rather than the settled spiral or elliptical shape a galaxy will eventually take after billions of years of mergers and gravitational sorting. Even at this early stage, it is producing prodigious amounts of ultraviolet light, more per unit of mass than most galaxies will ever manage again, because gas is abundant and star formation has barely had time to use it up or blow it away. A fraction of that ultraviolet light leaves the galaxy heading by chance in the direction that will one day be occupied by a small blue planet orbiting an unremarkable star. At the moment it leaves, that destination does not exist. The Sun has not formed. The Milky Way itself is still a scattering of separate protogalaxies that have not yet merged into a single structure. The light does not know or care about any of this. It simply travels outward at the only speed light can travel, carrying with it an exact record, frozen at the moment of emission, of what this particular patch of the young universe looked like. Everything that happens to that light between here and its eventual arrival, how far it appears to have travelled, how its colour changes, how long the trip actually takes, depends entirely on what the universe does to the space it is crossing. That is the story the next chapters take up. The light leaving that young galaxy is, at the moment of its birth, mostly ultraviolet, the same general kind of light a hot young star anywhere produces. What happens to it over the next 13.4 billion years is not that it fades exactly, and not that it simply gets stretched thin the way a beam from a flashlight spreads out over distance, though that happens too. Something more specific happens to its wavelength, the physical distance between one crest of the light wave and the next, and understanding that specific thing is the key to almost everything that follows in this account. Space itself, cosmologists have measured with extraordinary consistency for a century now, is expanding. This does not mean galaxies are flying outward through a fixed static space the way shrapnel flies outward from an explosion. It means the space between galaxies is itself growing, continuously, everywhere at once. A useful, if imperfect, way to picture this is a balloon with dots drawn on its surface, being slowly inflated. No dot is at the centre of the expansion, and no dot is moving across the balloon's surface under its own power. Every dot simply finds itself getting farther from every other dot, because the rubber between them is stretching. Galaxies play the part of the dots. There is no centre to this expansion that we could point a telescope at, and there is no edge either, as far as any measurement has ever found. Now put a beam of light on that stretching balloon, travelling from one dot toward another. As the surface beneath the light stretches during the trip, the light's wavelength stretches along with it in direct proportion. A wave that left as tight, energetic ultraviolet light arrives, after a long enough journey through enough expansion, stretched into visible light, then into infrared. The band of light just beyond what the human eye can see, felt more easily as warmth than seen as colour. This lengthening toward the red end of the light spectrum, cosmologists call it redshift, and it is not a metaphor and not a rounding error. It is a direct, measurable record of how much the universe grew while that particular beam of light was in transit. This is a genuinely different phenomenon from the redshift produced when a source is simply moving away from an observer through otherwise static space. The everyday Doppler effect, familiar from an ambulance siren, dropping in pitch as it passes. Both effects stretch a wave and both get called redshift loosely. But cosmological redshift keeps accumulating the entire time light is in flight, growing with every additional stretch of space it crosses, rather than depending only on a single relative velocity at one moment. A photon that has been travelling for 13.4 billion years has been stretched by every increment of expansion that happened during that entire span, which is why the most ancient light arrives shifted far more dramatically than light from anything nearby. This matters for more than colour, because that same stretching also drags out the light's arrival in time. A galaxy that briefly flared unusually bright for, say, 10 million years as it formed its first generation of stars would, if its light had to cross a large fraction of the observable universe to reach us, appear to flare for considerably longer than 10 million years, because the light emitted near the end of that flare has slightly less expansion left to travel through and slightly less distance to cross than light emitted at the beginning, so it does not catch up to compress the apparent duration. Instead, the expansion of space during transit stretches the whole event out. Astronomers call this cosmological time dilation, and it means that distant events genuinely appear, to every clock we can build, to unfold in slow motion. Redshift, in other words, is simultaneously a colour, a distance indicator, and a kind of stopwatch, all wound up together in the same physical stretching of space. Reading that one number correctly, and separating it cleanly from ordinary motion from dust and from a galaxy's intrinsic brightness would occupy astronomers for most of the 20th century, and the tools they built to do it are the subject of the next several chapters. Suppose you fire an arrow at a target that starts 20 meters away, but the target is itself being carried backward on a conveyor belt for the entire time the arrow is in the air. The arrow eventually reaches wherever the target has drifted to, but the distance the arrow physically flew is shorter than the distance to the target's current position when the arrow finally arrives, because the target kept receding the whole time the arrow was closing the gap. Light crossing an expanding universe faces a version of this same problem, except that in this case it is not the target moving on a belt through fixed space, it is the belt itself, the space between archer and target, that keeps lengthening throughout the flight. This is why a single measurement, redshift, ends up implying two legitimately different answers to how far away is that galaxy, and cosmologists use both, carefully labelled, because each answer is doing a different job. The first is called light travel time distance. Multiply the speed of light by the number of years the light actually spent in transit. For the most distant confirmed galaxy, that comes to roughly 13.4 billion light-years, a figure describing how old the light is, essentially a measurement of time dressed up as a distance. The second is called comoving distance, where that same patch of space has drifted to by now, accounting for every bit of expansion that happened during the light's entire journey, including expansion that happened after the light left but before it arrived. For that same galaxy, comoving distance comes out to roughly 33 billion light-years, nearly 2.5 times larger, despite describing the very same object and the very same beam of light. Neither figure is wrong, and neither is more real than the other. They are simply answering different questions. If someone asks how old is the light I am looking at, light travel time distance is the honest answer. If someone asks where is that galaxy right now, comoving distance is the honest answer, though even that phrase, right now, needs a careful definition in a universe without a single shared clock for every location at once, which cosmologists solve by using cosmic time as measured from the Big Bang, the same clock every observer in the universe would in principle agree on if they measured the temperature of the leftover glow from the Big Bang itself. Here is a way to hold the scale of that gap in human terms. Imagine mailing a letter to a friend who then spends decades slowly relocating farther and farther across a continent while your letter is in transit. By the time it finally arrives, forwarded through years of postal systems, the friend's current address is far beyond wherever they were standing when you dropped the letter in the box. Even though the letter itself only ever travelled the distance, the postal system actually carried it. The letter's travel distance and the friend's current distance are both true numbers, and confusing them, quoting one when someone asked for the other, is exactly the kind of error that made early newspaper reports of distant galaxy discoveries occasionally contradict each other by billions of light-years while describing the identical object. Working out either number reliably, though, requires something this chapter has not yet supplied, a way to trust that a given redshift really does correspond to a given distance, rather than to a nearby dusty galaxy that merely looks red for some other reason, or a foreground object masquerading as something far more remote. That trust had to be built rung by rung, over decades, using objects close enough to measure by more than one method at once. Building that ladder is where the next chapter goes. Redshift tells you how much a beam of light has been stretched. It does not, by itself, tell you how far away the object that emitted it actually is, because that conversion depends on knowing the detailed expansion history of the universe, which is itself something astronomers had to work out using distances measured a different way first. Solving that problem meant building what is usually called the cosmic distance ladder, a sequence of measurement techniques, each one calibrated against the rung below it, each rung reaching farther than the last, until the ladder finally reaches far enough to calibrate redshift itself. The first rung needs no assumptions about the objects being measured at all, only geometry. As Earth orbits the Sun, nearby stars appear to shift very slightly against the background of far more distant stars, the same way a finger held at arm's length appears to jump sideways when you close one eye and then the other. This apparent shift, called parallax, is larger for closer stars and smaller for farther ones, and because the size of Earth's orbit is known precisely, the amount of shift converts directly into a distance, no other assumptions required. Parallax is extraordinarily reliable, but it only works for stars close enough that the shift is measurable at all, a few thousand light-years at most, even with the most sensitive space-based instruments. To reach farther, astronomers needed an object whose true brightness could be known independently of how bright it merely appears from Earth, because comparing true brightness to apparent brightness gives distance directly, the same way you can judge how far away a lit window is at night, if you already know roughly how bright that kind of window's light actually is. Cepheid variable stars, a class of stars that pulse in size and brightness on a strict repeating schedule, turned out to solve this. In 1908, astronomer Henrietta Leavitt found that a Cepheid's pulsation period, the number of days between one peak brightness and the next, correlates tightly with its true brightness. Slower pulsing Cephids are intrinsically brighter. Measure the pulsation period of a Cephid anywhere, and you know its true brightness. Compare that to how bright it appears, and you have its distance, calibrated using nearby Cephids, whose distances parallax had already confirmed independently. This single relationship, a period luminosity law derived from painstaking measurements of thousands of variable stars, let astronomers measure distances to other galaxies for the first time, reaching tens of millions of light-years, thousands of times farther than parallax alone could manage. Cephids are bright, but even they fade below detection at the distances involved in the most distant galaxies. The next rung needed something brighter still, and the universe supplied one, a Type Ia supernova, the explosion produced when a dense stellar remnant called a white dwarf pulls in matter from a companion star until it crosses a specific mass threshold and detonates in a runaway thermonuclear reaction, because that threshold is essentially the same. Everywhere in the universe, these explosions reach very nearly the same true brightness at their peak every time, making them what astronomers call standard candles, objects bright enough and consistent enough to be usable as distance markers across billions of light-years. Their peak brightness was calibrated, in turn, against Cephids in the same host galaxies, tying this rung firmly back to the one below it. With the ladder's rungs calibrated against each other this way, distance and redshift can finally be compared directly for the same set of galaxies, distant enough to show meaningful redshift but close enough for a standard candle inside them to still be measurable. That comparison is exactly what let one astronomer working at an observatory in California in the 1920s notice something that would reorganize the entire field. The farther away a galaxy sits, the faster its light appears redshifted, in a strikingly consistent proportion. That astronomer was Edwin Hubble, and the discovery he made using this ladder is where the next chapter picks up. Using the distance ladder's calibrated rungs, Edwin Hubble compared the redshifts of galaxies to their independently measured distances and found a strikingly clean relationship. The farther away a galaxy is, the faster its light appears redshifted, and the relationship is close to a straight line running through the data. Published in 1929, this became known as Hubble's law, and its implication overturned a near-universal assumption. If every galaxy in every direction appears to be moving away from us, and more distant ones appear to be moving away faster, in exact proportion to their distance, the simplest explanation is not that we occupy some special center everything is fleeing from. It is that space itself is expanding uniformly everywhere, carrying every galaxy away from every other galaxy at once, exactly the balloon surface picture described earlier, now backed by measurement rather than analogy. Hubble had not merely found a curious pattern. He had found direct observational proof that the universe has a history, that it was smaller and denser in the past, and that tracing this expansion backward implies a beginning, a moment cosmologists would later name the Big Bang. Hubble's law, refined across the following decades by better instruments and more distant standard candles, became the working tool for converting a measured redshift into a distance, the exact conversion this account has relied on already, to state that the most distant confirmed galaxy sits some 13.4 billion light-years away in light travel time. But converting a redshift into a distance is only useful if you can find and measure the redshift of something that faint and that far away in the first place, and for most of the 20th century, the galaxies capable of setting distance records were simply the brightest ones astronomers happened to stumble across, not a systematic search for the faintest, farthest objects the sky actually contained. That changed in December of 1995, when the Hubble Space Telescope, named for Edwin Hubble himself, and orbiting roughly 540 kilometers above Earth, free of the atmospheric blurring and light pollution that limit ground-based observatories, was pointed for 10 consecutive days at a small patch of sky in the constellation Ursa Major, chosen specifically because it appeared to contain almost nothing. No bright stars, no known galaxies, nothing to distract from a pure test of how deep the telescope could see. The resulting image, called the Hubble Deep Field, revealed roughly 3,000 galaxies crowded into a patch of sky smaller than a grain of sand, held at arm's length, the overwhelming majority of them never before detected by any instrument, some of them among the most distant objects then known. The patch of sky had never been empty at all. It had simply been full of galaxies too faint for anything built before Hubble to register. The Deep Field campaign was repeated and extended over the following 2 decades, culminating in the Hubble Ultra Deep Field of 2004 and later composite images stacking hundreds of hours of exposure time on a single small patch of sky, pushing the detectable galaxy population back toward redshifts corresponding to less than 1 billion years after the Big Bang. Each of these campaigns worked on the same basic principle: point a telescope at one patch of sky for as long as possible, let faint light accumulate photon by photon over days or weeks of total exposure, and see what emerges from what would otherwise look like blank darkness. It is a method that trades breadth for depth, examining a tiny sliver of the whole sky in extraordinary detail rather than scanning the entire sky shallowly, on the logic that the universe is, on the largest scales, similar enough in every direction that one sufficiently deep look tells you what countless other patches of sky would also contain if examined this closely. What these deep fields could not easily do, at least not with Hubble alone, was confirm precisely how far away the very faintest, reddest smudges in the images actually were, because confirming a redshift with certainty requires more than an image. It requires spectroscopy, splitting a galaxy's light into its component wavelengths and finding the exact unmistakable fingerprint of a known atomic transition shifted by a known amount. For the faintest, most distant candidates the deep fields turned up, obtaining that spectrum would push existing telescopes to their absolute limit, and it would take a further 2 decades of refined technique, and eventually an entirely new telescope to do it with confidence. That refinement is where the next chapter turns. Finding a candidate for the most distant galaxy in a deep field image does not require a full spectrum. It can be done, cleverly, using ordinary imaging alone through a technique called the Lyman break method. Hydrogen gas absorbs ultraviolet light very strongly at wavelengths shorter than a specific threshold, called the Lyman limit, essentially blocking that light from getting through at all. A young, actively star-forming galaxy floods its surroundings with ultraviolet light above that threshold, but almost nothing below it. By the time that light has redshifted enough to reach Earth from a very distant galaxy, this sharp on-off boundary in its spectrum has shifted into visible or infrared wavelengths astronomers can image directly. So a galaxy that appears clearly in a red or infrared filter image, but essentially vanishes in a bluer filter, exactly at a wavelength that maps back to the Lyman limit, is very likely a distant galaxy, and roughly how distant can even be estimated from exactly where that vanishing point falls. This method let astronomers sift thousands of Hubble Deep Field galaxies for the small handful of candidates worth the enormous additional telescope time spectroscopy requires. Spectroscopy is the step that turns a candidate into a confirmed record, because a Lyman break alone can be mimicked by nearby dusty galaxies that merely look red for unrelated reasons, and a claimed record based on imaging alone has been embarrassingly overturned before. Spectroscopy instead spreads a galaxy's light out into its full range of wavelengths and looks for a specific, unmistakable signature, most often an emission line called Lyman alpha, produced when electrons in hydrogen atoms fall from one particular energy level to another and release light at one exact, well-known wavelength. Find that exact spectral feature shifted by a precisely measurable amount, and the redshift is confirmed with a level of confidence a broad imaging colour alone could never provide. In 2016, using this method with the Hubble Space Telescope and the large ground-based Keck Observatory in Hawaii, astronomers confirmed the galaxy GNZ 11 at a redshift of 11, meaning the wavelength of its light had been stretched to roughly 12 times its original length during the journey, corresponding to a galaxy seen as it appeared only about 400 million years after the Big Bang. It held the confirmed distance record for several years, an object surprisingly bright for something so early already actively forming stars, already large enough to be clearly detected across that enormous gulf of cosmic time. GNZ 11's redshift also marks something close to a practical ceiling for the instruments doing the confirming. Lyman alpha and most other useful spectral fingerprints, by a redshift around 10 or 11, have been stretched well out of visible light and deep into the infrared, a part of the spectrum ground-based telescopes struggle with badly, because Earth's own atmosphere is warm and glows brightly in the infrared, and water vapour in the air absorbs large stretches of it outright. Even orbiting above the atmosphere, Hubble's mirror and instruments were designed primarily for visible and near ultraviolet light, giving it only limited reach into the infrared wavelengths, where the earliest, most redshifted galaxy's light was arriving. pushing the redshift record meaningfully further than GNZ11 was not, at this point, a matter of looking harder with the same tools. It required an instrument built from the ground up to work in the infrared, cooled to temperatures where its own machinery would not drown out the very light it was trying to detect, and placed somewhere the atmosphere could not interfere at all. That instrument had already been in development for decades by the time GNZ11 was confirmed, and its story, and the specific physics of why infrared vision was the missing piece all along, is the subject of the next chapter. The deeper into the universes past a galaxy's light comes from, the more that light has redshifted, and this is not a coincidence or a quirk of a particular instrument. It is a direct, unavoidable consequence of how much the universe has expanded during the light's journey. A galaxy seen 400 million years after the Big Bang has had its light stretched by roughly a factor of 12. A galaxy seen closer to 300 million years after the Big Bang has its light stretched by closer to a factor of 15. Beyond a certain redshift, essentially all of a young galaxy's most useful light, the ultraviolet glow of its hottest young stars, has been stretched entirely out of the visible range human eyes, and most existing telescopes were built to see, and lands instead deep in the infrared, felt more naturally as warmth than seen as colour. Chasing higher redshift records is therefore not simply a matter of building a bigger version of an existing telescope. It requires an instrument fundamentally built around infrared light from the start. This is the specific problem the James Webb Space Telescope, launched on Christmas Day of 2021 as a joint project of NASA, the European Space Agency, and the Canadian Space Agency, was engineered to solve. Its primary mirror spans 6.5 meters across, built from 18 hexagonal segments coated in a microscopically thin layer of gold, chosen because gold reflects infrared light with exceptional efficiency, folded origami style for launch and unfolded once in space, giving it more than 6 times the light collecting area of Hubble's mirror. A larger mirror alone does not solve the infrared problem though, because any warm object, including the telescope's own structure, glows in the infrared and would otherwise flood its own instruments with light indistinguishable from the faint, ancient signal it was trying to detect. Solving that meant getting the telescope genuinely cold, and keeping it that way, without ever letting direct sunlight reach it. Webb orbits not close to Earth but around a gravitationally stable point called the second Sun-Earth Lagrange point, roughly 1.5 million kilometers from Earth, on the side facing away from the Sun, where the combined gravity of Earth and the Sun lets a spacecraft hold a stable position relative to both with minimal fuel. There, a 5-layer sunshield roughly the size of a tennis court, made of a thin reflective material, blocks heat from the Sun, Earth and Moon alike, letting the telescope's mirror and infrared instruments passively radiate their own heat away into the cold of space until they settle to around minus 233 degrees Celsius, cold enough that the telescope's own structure emits essentially nothing in the infrared wavelengths it needs to detect. One instrument, built to see slightly longer infrared wavelengths still, is cooled further, with active refrigeration, to nearly minus 266 degrees Celsius, only a few degrees above the coldest temperature physically possible. Every piece of that engineering, the size of the mirror to gather enough faint light, the sunshield and orbit to keep it cold, the cooling to keep the telescope itself from drowning out its own observations, exists to serve one specific scientific goal among several: to see infrared light too faint and too red for any telescope before it. From galaxies that existed when the universe itself was a small fraction of its current age. Within its first year of science operations, astronomers pointed it at exactly the kind of deep field its predecessor had pioneered decades earlier, and immediately began finding candidates that pushed well past GNZ11's redshift of 11. Confirming those candidates, and discovering just how surprisingly bright and mature some of them turned out to be, is where the next chapter goes. The JWST Advanced Deep Extragalactic Survey, generally abbreviated JADES, is a large observing program using the James Webb Space Telescope to image and take spectra of thousands of galaxies in 2 well-studied patches of sky, chosen in part because Hubble had already surveyed them extensively, giving astronomers a foundation of prior data to build on. Within its earliest observing runs, JADES turned up several candidate galaxies with colours suggesting extremely high redshift, exactly the sharp red-to-invisible transition the Lyman break method predicts for the most distant objects, but at redshifts high enough that confirming them with certainty mattered more than ever, Given how many earlier high redshift claims from less capable instruments had not survived closer scrutiny. Spectroscopic follow-up using an instrument aboard Webb capable of splitting the light of dozens of faint galaxies simultaneously into detailed spectra confirmed several of these candidates beyond reasonable doubt. Among them, a galaxy catalogued as JADES GSZ13 was confirmed at a redshift of 13, corresponding to a galaxy seen as it existed only about 325 million years after the Big Bang, decisively surpassing GNZ11's redshift of 11. Within roughly a year, further JWST observations pushed the record higher still, confirming a galaxy at a redshift near 14, corresponding to roughly 290 million years after the Big Bang, among the very earliest galaxies confirmed by any method. Each of these confirmations rested on the same Lyman alpha and related spectral fingerprints described earlier, measured with enough precision that the redshift, and therefore the distance, is not seriously in dispute among astronomers working in the field, even as the exact record continues to shift with each new observing run. What startled astronomers more than the raw distance record, though, was how bright and how structured some of these earliest confirmed galaxies turned out to be. The simplest pre-Webb models of early galaxy formation predicted that galaxies this soon after the Big Bang should be small, faint, and barely assembled, scraps of star formation rather than coherent structures. Several of the JWST galaxies, instead, appeared unexpectedly luminous for their distance, implying they had already built up a substantial population of stars, or were forming new stars at a startlingly rapid rate, or both within the first few 100 million years of cosmic history, a span some astronomers had assumed was simply too short for that much stellar mass to accumulate. This tension, sometimes described in the astronomical press with more drama than the data strictly demands, is not a crisis for the basic picture of the Big Bang or cosmic expansion, both of which remain supported by an enormous and independent body of evidence, including the very redshift distance relationship this account has spent several chapters establishing. It is, more precisely, a challenge to specific models of how efficiently gas turns into stars in the earliest galaxies, and how quickly the small clumps described in the first chapter of this account can merge and organize into structures bright enough to be seen across 13 billion years of cosmic history. Some astronomers have proposed that star formation in this era was simply more efficient, converting a larger fraction of available gas into stars per unit time than later galaxies typically manage. Others have suggested that a top-heavy mix of unusually massive, unusually bright stars, similar in spirit to the population 3 stars described earlier, could make these galaxies appear more luminous than their actual stellar mass would suggest. Both explanations remain active areas of research, and resolving which combination best fits the growing catalogue of confirmed early galaxies is one of the clearest examples of a genuinely open question at the frontier of this field, rather than a settled result. What is not in dispute is the redshift measurement itself, and what that measurement means for how far away, and how far back in time, these galaxies actually are, which the next chapter works through in careful detail. Return now to the two distances introduced several chapters ago, light travel time distance and comoving distance, and apply them concretely to JADES GSZ13, the galaxy confirmed at redshift 13. A redshift of 13 means the wavelength of the galaxy's light arrived stretched to roughly 14 times its original length, a small but important distinction from the redshift number itself, since the conversion factor is always the redshift plus 1. Feeding that stretch factor into the equations describing how the universe has expanded since the Big Bang, cosmologists calibrated the equations using exactly the distance ladder, and Hubble's law described earlier produces both distance figures at once. The light travel time distance comes out to roughly 13.4 billion light-years, meaning the light took 13.4 billion years to reach us, essentially the same figure as the age of the universe itself, since this galaxy formed only a few 100 million years after the beginning. The comoving distance, where that patch of space has drifted to by now, given every bit of expansion that occurred during the entire 13.4 billion year transit, comes out to roughly 33 billion light-years, more than double the light travel figure, because the universe has done a great deal of expanding during the intervening time. Holding that gap in human terms helps. Imagine a message sent from a ship that departs a harbour and sails outward for what would be, on Earth, a person's entire adult lifetime, say 60 years, at a steady speed. If the harbour itself were also drifting away from the ship's starting point for that entire 60 years, at a rate that itself increased the longer the voyage lasted, the ship's final position when the message finally arrives back home would be considerably farther from the harbour's current location than 60 years of the ship's own travel could account for on its own, because the harbour never stopped receding while the ship sailed. The message reports where the ship was when it was sent. The harbour, watching it arrive decades later, has to work out separately where the ship actually is now. Both figures are true, and confusing which one a listener is asking for produces exactly the kind of contradictory-sounding distance claims that occasionally make identical galaxy discoveries look, in casual reporting, like they disagree with each other by a factor of 2 or more. A further subtlety deserves a plain hedge here, because it is genuinely unsettled at the finest level of detail even though the broad picture is not. The precise numerical value of the comoving distance depends on exactly how fast the universe is expanding today, a quantity called the Hubble constant, which different measurement methods currently return slightly different values for, a persistent discrepancy astronomers call the Hubble tension. It is not large enough to change the story told in this account in any meaningful way, and it does not call into question that the universe is expanding, or that these galaxies are extraordinarily distant. It affects only the third significant figure of exactly how many billion light-years comoving distance comes out to, and resolving it remains one of the more interesting open problems in cosmology today. What is not remotely in doubt is the more fundamental point underlying every number in this chapter. Looking at JADES GSC Nasgiro is not looking at a place far away in the ordinary sense, the way a distant mountain is far away while still existing right now, exactly as you see it. It is looking at a moment, a specific snapshot of a specific patch of space as it existed 13.4 billion years ago, whose light has spent the entire intervening span of cosmic history in transit, arriving only now, carrying no information whatsoever about what has happened to that galaxy since. That galaxy, if it still exists in any recognizable form, has itself aged 13.4 billion years in the meantime, merged repeatedly with neighbouring galaxies almost certainly, and looks nothing today like the young, chaotic star-forming clump we are seeing arrive on our instruments. Every distant galaxy anyone has ever observed is, in this specific sense, a fossil, a perfectly preserved image of the past, arriving in the present, describing a version of the universe that no longer exists anywhere. That fossil quality is also what defines the outermost limit of what any telescope, however large, could ever observe, and that limit is the subject of the next chapter. JADES GSZ 13.0 is, at the time of this account, the most distant individual galaxy ever confirmed, but it is very far from the most distant thing astronomers have ever observed, and the gap between those two claims marks an important boundary. For roughly the first 380,000 years after the Big Bang, the universe was filled with a hot, dense plasma of unattached electrons and atomic nuclei, hot enough that any electron trying to settle into orbit around a nucleus was almost immediately knocked loose again by a passing photon. A plasma in this state is opaque to light in the same way a thick fog or the interior of the sun is opaque. Light does not travel freely through it. It scatters repeatedly off free electrons, bouncing in every direction almost as soon as it is emitted, unable to escape in a straight line to anywhere. Around 380,000 years in, the expanding universe had cooled enough to roughly 3,000 degrees Celsius for electrons and nuclei to finally combine into stable neutral atoms, a transition cosmologists call recombination, despite it being the first time these particular electrons and nuclei had ever combined at all. The moment this happened across the universe, the fog lifted. Photons that had been scattering endlessly suddenly had nothing left to bounce off and streamed outward freely in every direction, for the first time in cosmic history. That light is still travelling today, and it is the oldest light any instrument can ever, in principle, observe, because there is nothing to see before it. The universe before recombination was opaque, and no telescope built from any material can see through an opaque medium to whatever lies behind it, any more than a camera can photograph what is happening inside a thick cloud bank from outside it. Stretched by roughly 13.8 billion years of subsequent cosmic expansion, that ancient light has redshifted enormously, arriving today not as visible light at all but as faint microwave radiation, detectable across the entire sky in every direction at once, a nearly uniform glow astronomers call the cosmic microwave background. Its discovery in 1965, initially by two researchers at Bell Labs who mistook it for instrument noise, before realizing they had detected the afterglow of the Big Bang itself, remains one of the strongest single pieces of evidence that the universe really did begin in an extremely hot, dense state, precisely as the theory predicted decades earlier. Detailed maps of tiny temperature variations across this background, differing by only a few parts in 100,000 from one patch of sky to the next, encode the seeds of structure, the slightly denser regions that would go on, under gravity, to become the galaxies, clusters, and eventually the proto-galaxy described in the first chapter of this account. The cosmic microwave background is not, however, the absolute edge of the observable universe, only the edge of what can be seen using light. The true boundary, called the particle horizon, extends slightly farther still. It marks the distance, calculated using comoving coordinates in the same way JADES GSZ 13's 33 billion light-year comoving distance was calc to which light or any other signal has had time to reach us at all since the beginning of the universe, given how much space has expanded in the meantime. Current calculations place the particle horizon at roughly 46.5 billion light-years in every direction, meaning the entire observable universe, a sphere with us at its center by simple definition rather than by any special cosmic status, spans roughly 93 billion light-years across. Nothing beyond that boundary has had time to send us any signal whatsoever since the universe began, regardless of what instrument we might someday build, which raises an uncomfortable but genuinely important question. Is that boundary the edge of the universe itself, or merely the edge of what we personally happen to be able to see? That distinction, and what current evidence suggests about it, is where the next chapter turns. The particle horizon marks the edge of what light has had time to reach us since the beginning of the universe, but there is no strong reason to believe the universe itself simply stops existing at that boundary. The way a map's edge does not mean the land stops there, only that the mapmaker ran out of information. Every careful measurement of the large-scale geometry of space, most precisely from detailed analysis of the cosmic microwave background described in the previous chapter, finds the universe to be flat, or extremely close to flat, on the largest scales measured, meaning parallel lines in it stay parallel rather than eventually converging or diverging the way they would on a curved surface. A flat universe is consistent with being infinite in extent, though the measurements cannot rule out a universe that is simply very large but still finite, curving back on itself so gently across distances vastly greater than the observable universe that no measurement made from inside it could detect the curvature. Astronomers are careful and honest in saying this remains genuinely unresolved. The observable universe is, almost certainly, only a small fraction of however much universe actually exists, and no experiment currently conceivable can measure the difference between a universe that is merely enormous and one that is truly infinite. What compounds this problem rather than resolving it is a second and independently confirmed discovery. The expansion of the universe is not merely continuing, it is accelerating, with distant galaxies receding from us faster over time rather than at a constant or slowing rate, a result first established firmly in 1998 through observations of distant Type Ia supernovae, the same standard candles described several chapters earlier. The cause of this acceleration is attributed to something cosmologists call dark energy, a placeholder name for whatever is causing space itself to expand at an increasing rate. Its underlying physical nature is one of the largest open questions in all of physics, and this account will not pretend otherwise by dressing an unsolved problem up as a settled one. What the evidence does establish clearly, regardless of dark energy's ultimate explanation, is the consequence. Because expansion is accelerating, a galaxy sitting near the edge of what we can currently observe is, right now, receding from us fast enough that light it emits, today, will likely never be able to cross the ever-growing gap between us, even given infinite future time to try. This produces a genuinely strange, hedged, but well-supported prediction. Astronomers describe a boundary called the cosmological event horizon, distinct from the particle horizon discussed earlier. It marks the limit beyond which anything happening right now can never, even in principle, send us a signal in the future, no matter how long we wait, because the space between us and it is stretching faster than light emitted there could ever close the gap. Galaxies currently visible to us, including ones well inside the particle horizon, may in the very distant future gradually redshift into invisibility, and cross this event horizon as accelerating expansion carries them beyond it, their light stretched to wavelengths so extreme and so faint that no instrument, however sensitive, could ever detect it. The practical effect, many tens of billions of years from now, if current models of dark energy hold, would be an observable universe that has shrunk, in terms of how many other galaxies remain visible from within it, even as the universe as a whole keeps growing. None of this changes anything about JADES GSZ 13.0's distance measurement or the confidence astronomers have in it. That measurement rests on the light having already arrived, a completed transaction, not a prediction about the future. It does mean that the question of how much universe exists beyond what any telescope will ever see is, and very likely will remain, permanently outside the reach of observation, a genuinely humbling limit on what science can determine, distinct from the ordinary limits of instrument sensitivity this account has spent several chapters describing solutions for. Some boundaries, it turns out, cannot be pushed back by a bigger mirror or a colder detector. Having established both what can be seen and the honest limits of what can ever be seen, the next chapter turns back to record-holding galaxies themselves, and what their properties actually reveal about how galaxies like our own came to exist at all. Strip away the redshift measurements and the distance arithmetic for a moment, and ask a more direct question. What do these earliest confirmed galaxies actually look like, physically, as objects? The honest answer is that even James Webb's exceptional resolution shows most of them as barely more than a small, slightly extended smudge of light, a handful of pixels across, because their true physical size is genuinely tiny by modern galactic standards. Careful measurements of galaxies at these extreme redshifts typically find diameters of only a few hundred to a few thousand light-years, compared to roughly 100,000 light-years across for the disk of the modern Milky Way. If the Milky Way today were represented by a dinner plate, one of these earliest confirmed galaxies would be smaller than a coin resting near its edge, and considerably less orderly in shape. Rather than a settled spiral with clean arms, these early systems tend to appear clumpy and irregular, several distinct blobs of active star formation loosely bound together rather than one smooth, unified structure, exactly the chaotic proto-galaxy stage described at the very start of this account. What these tiny irregular systems lack in size, several of them make up for inactivity. Measurements of their light, spread out into a spectrum, allow astronomers to estimate how much of their mass is being converted into new stars each year, a quantity called the star formation rate, and several of the highest redshift confirmed galaxies show star formation rates strikingly high relative to their total mass, forming stars far more efficiently, pound for pound of gas available, than most galaxies manage today. This fits a broader pattern astronomers have found across the whole history of galaxy formation. Star formation activity across the universe as a whole appears to have peaked several billion years after the Big Bang and has been gradually declining ever since. As galaxies use up their available gas and merge into larger, more settled, comparatively quieter systems. The earliest galaxies, in other words, are not simply smaller, dimmer versions of today's galaxies. Many of them appear to be unusually vigorous for their modest size, precisely the kind of galaxies most likely to be bright enough to be detected at all across such an enormous distance, which is itself an important selection effect worth being honest about. The earliest galaxies we can see are, almost by definition, the unusually bright and active ones, not necessarily representative of every galaxy that existed at that time, many of which were likely fainter still and remain entirely undetected by any instrument built so far. Over the roughly 13.4 billion years separating that early era from today, galaxies like these do not simply sit still and grow old in isolation. Gravity continues its patient work, pulling smaller galaxies together into mergers, sometimes gentle and gradual, sometimes violent collisions that trigger dramatic bursts of new star formation as gas clouds from both galaxies collide and collapse. A small, clumpy, irregular galaxy from the early universe, astronomers' best current models suggest, is a plausible ancestor, several mergers and many billions of years removed, of a large settled spiral galaxy much like our own Milky Way, or of one of the giant elliptical galaxies found at the centers of large galaxy clusters today, built from the accumulated remnants of many smaller galaxies that merged and settled over cosmic time. This is not a claim that any specific confirmed galaxy is a direct, traceable ancestor of any specific galaxy alive today. The individual histories are far too complicated and far too poorly constrained by current data to draw that precise a line. It is instead the broader and well-supported picture that the small, chaotic systems astronomers can now observe directly, at the very edge of what any telescope can reach, are genuine examples of the raw material every large galaxy in today's universe, including our own, was ultimately built from. This reframes the entire search for ever more distant record holders as something more significant than a simple game of chasing a bigger number. Each confirmed galaxy a little farther back in time is a direct look at an earlier stage of the same general process that built the Milky Way, testing and refining the same models of star formation, mergers and galactic growth this account has described. What a still more distant record might reveal, and how close astronomers might eventually get to observing the very first galaxies of all, is where the final chapter of this account turns. Every record described in this account, GNZ11's redshift of 11 in 2016, JADES GSZ 13 zeros, redshift of 13 in 2022, and the still higher confirmations that followed within the next 2 years, represents a search that is very much still in progress, actively pursued by observing programs already using the James Webb Space Telescope's full capability. The theoretical frontier astronomers are working toward is not an arbitrary bigger number. It is a specific and scientifically meaningful target, the redshift at which the very first individual stars in the universe, the true population 3 stars described in the opening chapter, built from gas containing nothing but hydrogen and helium, with none of the heavier elements every subsequent generation of stars would eventually produce and scatter through space, might become detectable. No confirmed detection of a genuine population 3 star or an entire galaxy made overwhelmingly of them exists yet, and finding one definitively would settle a question that has stood open since astronomers first proposed these stars must have existed decades ago, based on chemistry alone rather than direct observation. Several upcoming and currently operating instruments are specifically positioned to push this search further. The Nancy Grace Roman Space Telescope, expected to begin operations in the second half of this decade, is designed with a much wider field of view than James Webb, trading some of Webb's extreme depth for the ability to survey far larger areas of sky at once, useful for finding the rarer, most extreme high redshift candidates that a narrow deep field might simply miss by bad luck of pointing. On the ground, an emerging generation of extremely large telescopes, with primary mirrors reaching 25 to 40 meters across, considerably larger than any optical telescope currently operating, are under construction and expected to begin science operations within the next decade, bringing light-gathering power that could support far more detailed spectroscopic follow-up of the faintest candidates these wide surveys turn up. None of these instruments guarantees a detection of true population 3 stars. The honest scientific position is that current models predict they should be detectable at achievable redshifts with sufficiently powerful instruments, but the actual discovery, if it comes, remains a genuinely open outcome rather than a certainty. Whatever the next confirmed record turns out to be, the 2-number answer this account opened with will very likely hold the same basic shape, a light travel time distance close to the age of the universe itself, because the earliest possible galaxy necessarily formed close to the very beginning, and a considerably larger comoving distance, reflecting how much the universe has continued expanding in all the billions of years since that light set out. That relationship between the 2 numbers is not a peculiarity of any one record-holding galaxy. It is a direct, permanent consequence of how an expanding universe works, and it will apply to whatever galaxy eventually claims the title next, and to whichever one claims it after that. Which returns finally to the question this account set out to answer. How far away is the most distant galaxy we have ever seen, really? The honest answer has never been a single number, because the question itself is really asking 2 different things at once. How old is the light, and where is the source of that light now? 13.4 billion years old, and roughly 33 billion light-years distant right now. Both true, both necessary, describing the same beam of light that left a small, clumpy cluster of newborn stars before the Sun existed, before the Milky Way had assembled into its current shape and arrived, after crossing a universe that never once stopped growing during the entire trip, on a gold-coated mirror built specifically to catch it. The distance was never really about space alone. It was, from the very first chapter, mostly about time. The most distant galaxy astronomers have confirmed is not a single number so much as a pair of them, and the space between those 2 numbers is the honest answer to the question this account set out to ask. 13.4 billion years is how long its light spent crossing an expanding universe to reach a mirror above the Sun-Earth Lagrange point. Roughly 33 billion light-years is where that patch of space sits at this moment, carried outward the whole time the light was travelling. Neither number is a trick, and neither is the whole truth without the other. What the search itself revealed may matter more than the record it kept breaking. Every deeper look found galaxies further along than the simplest models expected, bright, already structured, already forming stars in surprising numbers within a few 100 million years of the beginning of everything. The universe, it turns out, got organised faster than astronomers assumed it could. Somewhere beyond the current record, more light is still arriving, having left before the record holder even finished forming, still crossing space that is still stretching. A larger mirror, a longer exposure, or a more sensitive instrument will eventually catch some of it, and the number will change again. The way it has changed every decade since Edwin Hubble first proved the universe was expanding at all. What will not change is the reason the number keeps needing revision. The farthest thing anyone has ever seen is not a place. It is a moment, arriving late from very far away, in a universe that has never once stopped growing while the message was in transit.